Alright. Hello and welcome to what is this? This is week 4 of summer session. Right? I think it's week 4. Oh goodness. Yeah. Totally is. It totally is. Okay, okay, yeah, we're good. Yep, we're good. So yeah, exam 1 seemed to go well. I've got a couple things to say about that. Yeah, so I guess the first thing to say is the average on it. yes it is. It is a man bun. I used to actually have one back in grad school, and I've been stealth growing the top to be able to do a top knot. So I'm trying something trying something new. Exam 1 is in the books. Its average was crazy high, 92%. This is the second time I've ever had an exam average hit the A range. So the average was crazy high. You all did very well. And I just wanted to say a couple things. The first thing I want to say is awesome job. All right, well done, everybody who played the game, because you played to win and you won collectively as a class. So excellent, excellent job. The second thing, excuse me, I wanted to mention is now that exam 1 is in the books, normally you take a test and was there a timetable in the description already? I have no idea. Oh, I bet. Oh, I know. Oh, Jen. I actually know exactly. You're like, how did he know? I forgot to delete it. It's last. So anyways, sorry. First thing I wanted to say is good job. Second thing I wanted to say is that normally during a semester you take a test, you get it done, it feels good, and then you can kind of let down. Unfortunately for summer, my second piece of advice is start prepping for exam 2. You got to start getting ready for exam 2, and the reason is exam 2 is already less than 2 weeks away. It'll open a week from this Friday, and the other thing about exam 2 is it will be on chapters 5, 6, and maybe maybe a little from chapter 7. But as you've seen already, chapters 5 and 6 are quite a bit harder, more difficult than the material that we dealt with chapters 2 through 4. And so so you did great, and that's awesome. But now it's time to study even harder, because my guess is that most people were probably prepping for the exam and weren't spending a ton of time on chapter 5, which that totally makes sense. But chapter 5, all of chapter 5 and all of chapter 6 will be on the second exam. So now would be a chance to go back, review those lectures, really learn that material, because again, our next exam is 2 weeks away. Here, hang on 1 second. I think I gotta turn the air conditioning on. Sorry about that. I was like sitting here lecturing, and I was like, it feels kind of warm, and my baby's upstairs taking a nap, and if it's warm for me downstairs, it's got to be even warmer for him up there. And turns out I did actually forget to turn the air on. Okay. Okay, so as far as all questions about exam 1, I'm going to need to wait to answer those until either after lecture, if we have some time, or in office hours tomorrow, just because we're a little bit behind on lecture, not crazy behind, but we definitely need to stay on pace. So let's see if we have time at the end of lecture today for some exam 1 questions. If not, then we'll hit it in office hours on Monday. Not Monday. Today's Monday. On Tuesday. All right. So totally. And okay, so one comment that I will make about exam 2, Brianna, you were saying that you're already feeling nervous for exam 2. Here's the thing, that's not necessarily a bad thing, that feeling, but what you do with it can be good or bad. If you let that nervousness lead you to procrastinate or not think about it, or kind of put things off, or paralyze you, it'll be a very negative thing. But if you take that anxiety, that nervousness, and say, okay, I'm feeling nervous, well, what's the cure for that? I'm going to study, and use that as a motor to bring you to the material, to interact with the material, it'll actually be very positive. So don't be debilitated by that experience. Use that as fuel to power your study engine. And then maybe exam 2 will be just as happy as exam 1. Alrighty. Alright, with that being said, we are in chapter 6. We've been talking about stoichiometry. And there we go. We left things off on Thursday, where we came to a realization that our stoichiometric coefficients were actually molar quantities. So, for example, let's look at the combustion of hydrogen again. All right, so 2 moles of hydrogen reacts with 1 mole of oxygen to produce 2 moles of water. All right. Okay, so now, here's my question. So here's this equation is already balanced. My question is, if you have 1.0 grams of hydrogen and they react completely, how many grams of oxygen will you, of water will you produce? All right, if you start with 1 gram of hydrogen, how many grams of water will you make? And the important thing to remember is these stoichiometric coefficients right here. These are mole to mol ratios. All right? They tell you the ratio of moles of reactant to moles of product. They're not mass ratios. In order to use these as a conversion factor, we need to first convert our mass of hydrogen to moles. All right? The picture is the first step that you want to do is take your grams of hydrogen and convert this to moles of hydrogen. Then you can use the chemical equation to convert from moles of hydrogen to moles of water. And then finally, you can convert from moles of water to grams. What you use here is the molecular weight, right? The AMUs. That is what allows you to convert from grams to moles. Oops. All right. And then what allows you to convert from moles of one substance to moles of another is the balanced chemical equation. All right, so that's how you want to think of this. Whenever you're given a mass of one thing and ask for the mass of another, first you go grams to moles, then moles to moles, and then from moles back to grams. Let's take a look at how to do this now. Just give me one second while I rewrite our balanced chemical equation. All right, so first, we have 1 gram of hydrogen. Before we can use our balanced chemical equation, we need to convert from grams of hydrogen to moles of hydrogen. And the way you get that unit conversion is with the masses from the periodic table. Hydrogen has an atomic mass of 1.01. And then here we have 2 hydrogen atoms. So so we have another hydrogen atom. The sum of these two masses is 1.02 AMU. And here's the important thing to remember, right? As we've already discussed, atomic mass units are the same as grams per mole. So this is literally 2.02 grams of hydrogen are in 1 mole of hydrogen. All right, and that is what we're going to plug in here for a unit conversion, because a 1 mole sample of hydrogen has a mass of 2.02 grams. All right, now grams of hydrogen cancel grams of hydrogen. Next, now that we are in units of moles, we can convert from moles of hydrogen to moles of water. And every time you have a mole to mole ratio, you get this ratio straight out of your balanced chemical equation. It'll be different every time. It'll be different for every chemical reaction. But you get that by looking at the stoichiometric coefficients for hydrogen and water. This balanced chemical equation tells us that 2 moles of hydrogen produce 2 moles of water. All right, so now moles of H2 cancels with moles of H2. And we need to, for a final unit conversion, convert between moles of water and grams of water. All right, now here, once again, we need to determine how many grams of water are in 1 mole, and we do that by adding up all the atomic masses. Oxygen has an atomic mass of 16.2 0.00. Same with yes, Susan, I can. Oh, which part in particular? Was it the part with the AMU in grams per mole? So when you add up the atomic masses for water, we have 2 hydrogens, right? So we got to multiply that one by 2. Oxygen is 16.00. So the atomic mass. Ah, yes. Okay, yes. Totally. So wherever, so here, give me 1 second. So here's the thing to keep in mind. The balanced equation tells you your mole to mole ratios of each, I should say between each of each reactant and product. So the balanced chemical equation literally tells us, oops, that 2 moles of H2 react to make 2 moles of H2O, and that allows us to write a conversion factor of 2 moles of H2 over 2 moles of H2O, or 2 moles of H2O over 2 moles of H2. So whenever you're converting between moles of one thing and moles of another, the unit conversion comes from the balanced chemical equation, because the balanced chemical equation tells you how many moles of one thing it takes to make how many moles of another thing. Does that make sense? And that's where, for example, this comes in. That's where this comes in. That mole to mole ratio comes from right here and right here. Okay, awesome. So now we have you'll notice here real quick, moles of water cancels with moles of water. Of course, anytime. The only unit left standing is grams of H2O, so now we can multiply everything through. Just getting a blank slate underneath. So now let's crunch our numbers. We have 1 divided by 2.02 times 2 divided by 2 times 18.02. So my calculator is giving me an answer, a value of 8.92079208. Sig Figs wise, my molecular weight for water is 4. My molecular weight for hydrogen is 3, but my initial mass is 2, so I can only keep 2 sig figs. So that means that my correct value with the correct number of sig figs will be 8.9. Correct units are grams of water. So 1 gram of hydrogen gas will produce 8.9 grams of water. Okay, this is super important just to make that point over again. It's that the ratio in your balanced chemical equation is a molar ratio. So it's a 1-to-1 ratio, but that's of moles of hydrogen to moles of water. You can see that the mass ratio is different. 1 gram of hydrogen didn't produce 1 gram of water. It produced almost 9 grams, right? 8.9. So you can only use your balanced chemical equation to convert between moles of a substance. Do we need to note? Susan, great question. Yeah, you don't need to mention whether it's a solid, liquid, or gas in the answer. All right, now this quantity has a name. We said if you have 1 gram of hydrogen, how many grams of water will be produced? And this is called the theoretical yield. All right, the theoretical yield. It's how much water you could theoretically produce using 1 gram of hydrogen. All right, so let's do another example. Karenza, great question. So 1.0 grams of H2 will react to produce 8.9 grams of H2O. So it's not that 1 gram of hydrogen equals 8.9 grams of water. It's that in this reaction, 1 gram of hydrogen will react to produce 8.9 grams of water. All right, let's do another example. So here, let's do a next level type problem. So iron 3 oxide, of course, reacts with aluminum metal to produce aluminum oxide and iron metal. All right, now this problem has 2 parts. Part A, write a balanced chemical equation for this reaction. Part B is if 5.00 grams of iron 3 oxide reacts with excess aluminum determine the theoretical yield of iron metal in grams. And then there is a part C to this problem. Oops. Hang on. Cancel. There we go. There's a part C to this problem, but I'm not going to say what it is yet because we haven't introduced that concept. So we'll get back to part C. All right. So this may seem a little like a lot to process. Sorry, that's my wife, who's working right now. She's sending me a text. Okay, so this may seem like a lot to process. This is kind of like a next level problem. This is the kind of stuff that you're going to be handling on the regs by the time exam 2 hits. So we've got a couple weeks, right? We've got like 11 days. So now's not the time to rest on your exam 1 score. Study as if your life depends on it, because exam 2 is on its way. First, let's balance this chemical equation. So you'll notice that we have a reaction between iron 3 oxide and aluminum metal. And this is going to produce aluminum oxide aluminum oxide and iron metal. All right, let's figure out what these things are. The cool thing about iron 3 oxide is it's a transition metal, so they tell us what the charge on iron is going to be. All right, it's +3. Oxide, we figure out oxide's charge from the periodic table. It's -2. Now we've got 2 charges, right? A +3 and a -2 that don't go into each other evenly. When this happens, we've got a quick and easy trick, right? The charge of the anion becomes the subscript of the cation, and the charge of the cation becomes the subscript for the anion. So iron 3 oxide will be Fe2O3. All right. Now let's look at aluminum metal. Aluminum metal is easy. Anytime you see that word metal following an element's name, that just means that it's that metal in its elemental form, so it's just Al. Right, that's aluminum metal. Iron 3 oxide plus aluminum metal produces aluminum oxide. Now aluminum's charge from the periodic table will be a +3, oxygen's a -2. We've got the exact same story with aluminum and oxide that we did with iron 3 oxide, right? We're going to use the anionic charge as a subscript for our cation, the cationic charge for the subscript of our anion. So aluminum oxide will just be Al2O3. Then again, we're dealing with iron metal. That just means we have Fe, all right? So we're not quite there. We need to write a balanced chemical equation, but we have determined what our reactants and products are for this reaction, all right? Now we have to balance it. Every time I balance, I just do it the slow way because it's the only way my brain can keep track of everything. We've got an inventory of iron, oxygen, and aluminum atoms. On the reactant side, we've got 2 iron atoms, 3 oxygen atoms, 1 aluminum atom. On the product side, we have 1 iron atom, 3 oxygen atoms, and 2 aluminum atoms. So we've got a couple things we need to balance. We have 2 aluminums on our product side, only 1 on our reactant side, so we need to multiply Al by 2. All right, this balances our aluminum count. You'll notice we have the same situation going on with iron, just on the other side of the reaction. So we need to multiply Fe by 2 to balance our iron count. Now you'll notice we've got 2 iron, 3 oxygen, and 2 aluminum on both sides of our chemical equation. So this is our balanced chemical equation, and we have completed part A. All right, part B for this reaction tells us, we're told that we have 5 grams of iron 3 oxide, and we're asked to find the theoretical yield we're asked to find the theoretical yield for iron metal, right? Now this is going to take us through the exact same process that we went through with the previous problem. Here we're given a mass, 5.0 grams of a reactant, and we're asked to find the grams of product that this could produce, all right? We know that there is a 1 to 2 molar ratio between iron 3 oxide and iron metal, but to use our molar conversions, our mol to mol ratio, we first start by converting our mass of iron 3 oxide into moles. So we're going to put grams of iron 3 oxide. Hang on. Sorry, my computer's. There we go. There we are. So our mass of iron 3 oxide in the denominator, moles of iron 3 oxide in the numerator. All right. Now, we need to calculate what this molecular mass is going to be, right? And let's see, do I have? There we go. Reaching for my textbook periodic table because it's the closest thing to me. Let's stick that right there. So iron is 55.85. Oxygen is 16.00. But you got to remember that we're dealing with 2 iron atoms and 3 oxygen atoms. So we got to multiply the 55.85 by 2 and the 16.0 by 3. All right? So let's see, 55.85 times 2 plus 16 times 3 is 48. So this will be 159.70. Remember that last sig fig has to be in the second decimal place. So 1 mole of iron oxide has a mass of 59.70. And grams of iron oxide cancels grams of iron oxide. Next step, because we're trying to get to our mass of iron metal, we need to convert from moles of iron 3 oxide to moles of just iron. All right, and this comes from our balanced chemical equation. 1 mole of iron 3 oxide will produce 2 moles of iron metal. So those units cancel. All right, now our last step, we need to convert from moles of iron to grams of iron. And the cool thing here is we can just look up the atomic mass for iron on the periodic table. 1 mole of iron has a mass of 55.85 grams. Now moles of iron cancel moles of iron, and we're ready to crunch our numbers. So let's see here. We have 5 divided by 159.70 times 2 times 55.85. All right, so the value that I'm getting for my mass of iron is 3.49718.222. Sig figs wise, I have 1 atomic mass with 4 sig figs, I have a molecular mass with 5, and then I have a mass of iron that just has 3. So I need to round to 3 sig figs. My 7 is going to round up. That rounds my 9 to a 10, which rounds my 4 to a 5. So 3.5 is the correct value after rounding. However, I still need 3 sig figs, so I'm going to put a 0 there. Then I need my units, which are grams of iron metal. All right, so 3.5 grams of iron metal is the theoretical yield. All right, so everybody tracking so far? Just give everyone a moment to process. Okay, now okay. So I want to pause for a second and talk about the theoretical yield. Oh, okay, Kate, sorry. Great question. Excellent question. Okay, so let's pause for a moment. Kate has a question which is, the answer to which is super important. The question is, why don't we use sig figs with moles? Because if you look at the calculation we just did, the mole to mole ratio, it looks like those numbers only have 1 sig fig in them, so why aren't we rounding to 1 sig fig at the end of the problem? And the answer to that question is in a balanced chemical equation, or it's in a balanced chemical equation, the mole to mole ratios is not a measured quantity. All right, the mole to mole ratio is not a measured quantity. So for this reaction, for example, the reason why we have 1 mole of iron 3 oxide producing 2 moles of iron atoms, it's not because this was measured. This was just based on balancing the chemical equation, right? Which is based on pure logic. This is a theoretical system. This was not measured. This is just based on we have to have the same number of atoms. And that's where those ratios came from. So it's not a measured quantity. And because it's not measured, that means the mole to mole ratios will never limit sig figs. All right, it'll always be your masses, not your moles. Kate, excellent question. Okay. Okay, so with that being said, was there something else? No, I think that's it. Okay, so they'll never limit our sig figs. Now, I want to park for a moment and think about this quantity we've been talking about, theoretical yield. All right. Now, the theoretical yield is the maximum amount of a product that can be produced by a chemical reaction. All right, and just as an FYI, from here on out, I'm going to be abbreviating the word reaction like this. All right, so that'll be reaction from this moment forward. So theoretical yield is the maximum amount of a product that can be produced by a chemical reaction, and this is contrasted with something called the actual yield. All right, the actual yield, in contrast to the theoretical yield, is the amount of a product the amount of a product that a reaction produces in lab. All right. The reason why we've been calling the numbers we've been calculating for how much product of how much water is produced 2 examples ago, and the last example, how much iron atoms, what's the mass of iron produced? We call those theoretical because that is the most possible based on what we started with, all right? But often when you're in lab, things don't go according to plan, right? Things are often kind of off, like there's human error, there are inefficient reactions, there's all sorts of ways that prohibit you as a scientist from isolating the maximum amount, the theoretical maximum that a reaction can produce, all right? And so that's where an actual yield comes in. The actual yield is how much is produced. The theoretical is how much can be produced. And there's a ratio, a quantity that is a ratio between the theoretical and actual yield called the percent yield. All right? And percent yield is equal to the actual yield divided by the theoretical times 100. All right, this is the percent yield. All right, it's equal to the actual yield divided by the theoretical yield. And with this in mind, now I can give you part C to the previous example. Remember how I said there's a part C with a question mark? This is what that part C of that problem would look like. And that is determine the percent yield for this reaction if the actual yield was 3.28 grams of iron. Oh, nightmares of exam 4. Yes, totally. Yes, so this is a concept that actually gets introduced in lab before lecture, and so now maybe you could also understand a little bit better my warning of like exam 2 is going to be harder. This is part of the reason why exam 2 will be covering material that you saw on lab 4. Carolyn, I'm sorry to hear that lab 4 is the most painful academic experience you've been through, but it might be topped by exam 2. Who knows? All right, now let's solve this last part. Percent yield is equal to the actual yield over the theoretical times 100. Totally. I love the lab 4. I think hurt a lot of people's souls. Some of them are no longer with us. Actually, at this point, a lot of people dropped after that one. We'll see what happens after test 2. So, to solve this, yes, Susan, absolutely. I do mean iron. I didn't mean to do it in red. Iron, not fluorine. 2 very different things. Okay. So here, So let's take a look at this. Our actual yield, you'll notice, is given to us in the problem, right? It was 3.28 grams. Our theoretical yield was actually calculated. We calculated the theoretical yield in part B, right? And in part B, we found that the theoretical yield was 3.50 grams of iron. So we have our numerator and denominator. All we have to do is plug them in and determine our answer. So we have 3.28 grams of iron divided by 3.50 grams of iron. Yeah, totally. It is crazy that people dropped. Multiply that by 100. So 3.28 divided by 3.50 times 100 gives us, so our value here is going to be 93.714287. Sig Figs wise, we can keep 3, right? We've got 3 in our denominator, 3 in our numerator. Keeping our first 3, our 1 is going to round down. So our answer will be, we have a percent yield of 93.7%. All right, and that is the answer to part 3. All right, let's see. How are we doing? Okay. Actually, not too shabby. Not too bad at all. Okay. So, what I want to do in our last 7 minutes together, I want to set up a problem. I'm going to set up this problem. I don't think we'll have time to actually do it all today, but then we'll pick up with this. We'll pick up with this. We'll pick up with this on Tuesday, tomorrow. I'm not sure. Before we do, Brianna has a great question. Will we always be given the actual yield? The answer is maybe. Look at this equation. Percent yield is actual over theoretical times 100. Now, Brianna's question, will we always be given the actual yield? The answer is no, I don't have to give you the actual yield. Which might sound terrifying. But just stay on the line for a minute. All right, you'll notice this equation has 3 variables, right? There's 3 variables. There's percent yield is 1, actual yield is 2, theoretical yield is 3. I can ask you about any one of these quantities as long as I give you a way to find the other 2, right? So let me show you what I mean. In the previous problem, it was given that you had actual and theoretical So what did I ask for? Well, I asked for percent yield. Right? You had the other 2, you could find percent yield. Let me ask you this. What if it was given in a problem? What if you had your actual yield? What if I gave you your actual yield and I gave you your percent yield? What could I ask for? Well, if I've given you actual and percent yield, then I could ask you for theoretical. Right? There's a third scenario. What if it was given that you had the theoretical and the percent yield? In this scenario, what could I ask you for? Well, in this scenario, I could ask you for the actual. So to say that, to ask, will we always be given actual yield? Not necessarily, but here's what I can promise you, and this is actually, when you stop to think about it, more comforting. You will always have, you will always know two of the three variables. And be asked for the third. Can I do an example for finding the actual yield? Yes. Yeah, it is exactly like... Oh my gosh, Peyton, that's awesome. It is 100... Peyton summarized it perfectly. She said it is like the density problems, but on some serious drugs. That is exactly it. Mathematically, it's no different than the density problems, right? One equation, three variables. You got to have access to two and find the third. Susan, yes, and actually, I think that would be a great way to close out. So here, let's do an example together. We're going to end on this note. So check out the following example. For the sake of time, I'm just going to what? Okay, so check this problem out. I'll just write it out. And as is, it's not balanced. But now it is. All right, so step number one would be, I would ask you to balance this thing, but for the sake of time, I'm giving that one to you. So step one, part A would be balance. Part B would be if 1.00 grams of oxygen reacts completely, what is the theoretical yield of water in grams? And then part C, looks like an E, part C would read like this. oops, not in yellow. The percent yield of this reaction was 88.22%. What was the actual yield? All right, so let's tackle this. I've done part A for us. I've written this balanced chemical equation, which is CH4 plus 2O2 produces 2H2O plus CO2. Part B says that we are given 1.00 grams of O2, and we're asked to determine the theoretical yield of water. All right? To do this, we're going to use our balanced chemical equation, but that is only good for converting between moles and moles. So first, we need to convert our mass of oxygen into a quantity with units of moles. All right? So oxygen has an atomic mass of 16.00 mu, right? And we're adding two of these together. So this is 32.00 AMU. That's what goes into our denominator here. Now grams of oxygen cancels grams of oxygen. Next step, we got to convert from moles of O2 to moles of H2O. All right. Now, from this balanced chemical equation, 2 moles of oxygen produce 2 moles of water. Moles of oxygen cancel. And our last unit conversion is from moles of water to grams of water. All right. And here for water we have hydrogen plus oxygen, right? So this will add to 18.02 grams per mole, and that is what we use to convert from moles of water to grams of water. Now we're ready to crunch our numbers. So we have 1 divided by 32 times 2 divided by 2 times 18.02. So our value is 0.563125. And Sig Figs wise, our molecular mass for both oxygen and water have 4 Sig Figs, but our mass only has 3, so we have to round to 3. So this will be 0.563 grams of water. This is our theoretical yield. All right, that's part B. Now for part C. All right, part C, we're given a percent yield. Right, we're told that the percent yield of our reaction is 88.22. And so we're going to use this equation for percent yield to solve, right? We've been given our percent yield. we've determined our theoretical yield in the previous problem, so we can solve for our actual yield. All right, we were given a percent yield of 88.22. This is equal to our actual, which we do not know yet, over our theoretical of 0.563 grams times 100. Now we need to get our actual yield isolated on one side of this equation, so we need 100 to cancel. We'll put that in the denominator, and we need 0.563 grams to cancel. That goes in the numerator. Then whatever we multiply by one side of the equation, we have to multiply the other side by the same thing. So here 100 cancels with 100. 0.563 grams cancels 0.563 grams. And we get our actual yield. Sorry, this is a mass. Is equal to 88.22 times 0.563 grams over 100. Let's crunch these numbers. 88.22 times 0.563 times, nope, not times, divided by 100 is 0.49668786 grams. Sig Figs wise, we're limited to our mass, right? That has 3. Our percent has 4. We're limited to the fewer, right? The 3. So we count off 1, 2, 3. 6 is going to round up. So the actual yield here is 0.497 grams of water. And that is our actual yield. Alrighty. So, Susan, that is the long answer to your question. Can we do an example where we find our actual yield? And there it is. And you can see we were given to do that in the problem. We were given our percent and our theoretical and asked for the actual. The fun thing was we actually weren't even given the theoretical. We found the theoretical in the previous part of the problem. So go us. Totally. Okay. This is an excellent spot to close off lecture for today. We are yes, totally. It's a lot of time to take up on an exam. Brianna, Brianna. That is an astute observation. Exam 2 will probably have fewer problems, but there's also probably going to be a time crunch with it. So that's just something to be prepared for. Let's see. I'm just looking at where we are. Okay, we're actually not doing too shabby. We're going to continue. Oh, wait. Come back. So, let's see. Thursday exam 2. Thursday. Oh, is this from Kate? From wait, what did I say? Yeah, from lecture. Totally. So I will take a look at it. We might be able to cover it tomorrow in lecture. If not, we can definitely go over it in office hours. It'll partially depend upon. I kind of need to assess where we are in chapter 6 to see if we'll have time. So if we can't tomorrow in lecture, we definitely will in office hours. I know we opened up with a couple people had questions on exam 1, but let's go ahead and save those for office hours, just because today my wife is at work, which puts me on baby duty, and I've got to get him up from his nap. Anyways, so I will get back. So in office hours tomorrow we'll have plenty of time to talk about all the exam questions that you have. Any possibly, if we don't have time in lecture to do that exam 2 level question from last week, we can hit that there. Totally. So let's see. Are there other for lab quiz 5? Is it similar to quiz 4 in terms? Okay, so yes, totally. Parthana, thank you for being patient. I so appreciate it. Carenza had a question about the lab 5 quiz. It is lab 5 quiz. Let me just take a look at it really quick. It's been I didn't write the 5th lab quiz. I read it, I proofread it, all that stuff. But let me just take a look at it, because it's been a minute. Right. So lab 5 quiz test for so it's the chapter 5 stuff, or sorry, the lab 5 stuff deals with Lewis structures, Vesper geometries, bond polarities, molecular polarities, all that kind of stuff. So that's what you're going to expect. There's not a lot of calculations, but other than like counting electrons to figure out how to build a Lewis structure. Okay, cool. So let's go ahead and press pause here. We'll come back tomorrow. Of course, anytime. We'll come back tomorrow with more chapter 6 lecture, and then answering questions to our heart's contents in office hours. Sorry for spacing out. It's great to see everybody again. Have an awesome Monday. Check out the playlist. It's nice and chill. And I'll catch you all tomorrow.